All right. Okay, hi everybody. So I gave myself 4 topics to discuss in my 4 hours of lecture, and we only did one last week, so I'm going to be a little bit rushed today, but I want to get you all done on time. So the 3 things we're going to review today are the spectrum of fault slip rates, which I think Yajing talked about a bit during her lectures from more of a seismological or geodetic standpoint. And so I just wanted to fill in and talk a little bit more geologically about what that means for the rock record. Then I thought I'd give an overview of subduction faults, since like a lot of the faults that we've talked about have been in continental crust. I thought it'd be interesting to look at the overall architecture and what the deformation regimes are in subduction zones. And then I'm going to finish with some stuff that's hopefully going to be a little bit of a review from your introductory structural rheology class, but just talk about stresses and the role of fluids in affecting stress in faults and how that affects fault behavior. And I'm actually not going to get to induced seismicity at all, but if you remember the theory behind how pore pressure affects faulting, then induced seismicity is pretty easily explained using that theory. Okay, so can everyone hear me? Is there anybody having any troubles? Yeah, you guys are all muted, so I'll just keep talking. Send me a text if you can't, if I go too fast or you can't hear me. So, okay, this is a big problem in all, I think, observational fields, but I just wanted to bring it up with respect to the faulting that we started talking about last week, is understanding scaling relationships. So, actually what Yajing and I spent a lot of time talking about is what can we learn about earthquakes from her studies, which are modeling or looking at seismic waves, that we can actually apply to an outcrop study in the rock record and vice versa. So the biggest problem there is that the earthquakes that are interesting to study, because we have enough data about them and enough information, they involve rupture areas that are on the scale of hundreds of meters or kilometers. So it's a pretty rare outcrop exposure kind of context where we would actually be able to see the whole area of an earthquake rupture. You know, we do detect things like 1s and 2s that might have smaller ruptures, but in general, and when we're looking at an outcrop, we're looking at some kind of like very tiny window into whatever the physical area involved in the earthquake might be. Can somebody close that door? Yeah. Thanks, John. So the same problem arises when we think about what we can do in the lab, laboratory experiments, and analog models. There we have a couple of additional scaling problems, because not only are experimental setup or like a sandbox or a friction apparatus or whatever is going to have a little tiny fault that's on the scale of centimeters or tens of centimeters, but the material properties of those materials and the strength of gravity and things like that, those things don't scale. So if you take something of a certain strength and deform it on a very small scale, how do you scale that up to a very large scale? Is it important that you scale things like the viscosity, and how do those relationships work? And then in terms of the earthquake problem, again, we're going to talk a little more about the spectrum of slip behaviors today, but we'd like to know if fast slip is really actually different than slow slip. It's very different for us on the human time scale when we talk about plate rate creep at centimeters per year versus, you know, centimeters per second in an earthquake. But from the rock record standpoint, how are those things different? How can we tell them apart? Are there hard lines between all earthquakes are a meter per second and then the other kind of deformation we have is plate rate creep? Or are we looking at behaviors of the earth that could span all the deformation rates in between? How we figure that out? Those are the kind of questions that we have to think about when we're looking at the rock record to understand active tectonic behavior. So this is a question that Ide et al. Asked in 2007, and they made this plot, which has become like the whole workshops are convened around this plot. Like this has been a really influential plot. So on the x-axis, we have the log of the seismic moment. So that's basically a measure of how much energy is involved in a slip event on a log scale. And on the y-axis, we have the characteristic duration, also on a log scale. So that 0 would be an event that takes 1 second, and 7.5, a power of 7.5 seconds would be how long a slip event that lasts for 1 year. So this is kind of a rate or time versus energy plot. And so this plot is actually made into a cartoon. The original has lots of different dots on it, but these zoned areas are shown that correspond to lots of events. So the first thing to notice is that regular earthquakes fall on one single line. I hope everyone can see it. It's showing up kind of faint on our screen. Where do I get the, oops. Uh-oh, where do I get the drawing tools? Oh no, I don't know where they are. Nope, help, nope. Okay, anyway, regular earthquakes, they're very quick, so they fall in low numbers on the time scale, on the duration scale, and they can span all the entire range of energy. So they can go from very tiny earthquakes that have a very small seismic moment to very large earthquakes with a giant seismic moment, but they're all short in duration, so they're quite fast. And then the slow earthquakes, so these are basically events that occur on similar faults and have similar rupture areas to regular earthquakes, but they just take a really long time. They go at different rates. They span a much greater range of durations, and little names for different types of them are on here. Low frequency earthquake down at the bottom near the origin. Moving up the red line, we have very low frequency earthquakes, slow slip events, episodic tremor and slip, silent earthquakes. So these are things that in general, except for the LFE and VLFE, they are too slow to generate seismic waves that are captured by seismometers. A lot of these are detected by finding ground motions that extend over a period of time with the geodetic networks. And so Ide et al. Colored in this gray triangle gap where they said, okay, we have fast earthquakes and then we have slow earthquakes, and there's basically nothing in between. Okay, so this plot is from Peng and Goldberg in 2010, and it's basically the same plot. Duration on the y-axis, seismic moment on the x-axis. Here you can see some of the more detailed data that went into defining these regions for regular earthquakes and slow slip. And what you start to see, especially down toward the lower left corner of the plot, is that there's a lot of different events, blue squares, purple square, red star, that start to fall between these two lines. And in fact, it's what the case that Peng and Gomberg made, and that Joan Gomberg's been kind of making over a series of talks over the last few years, is that there's an instrumental gap between these two types of events, where we're not picking up necessarily the radiated energy from a particular event. That doesn't mean that particular type of event doesn't exist. So she's actually been arguing that all of the slip rates that are possible in the Earth are actually happening, and that we don't have two distinct types of slip rates. But it's, yeah, if you have time, it's really interesting to go through these and see what all of these different types of events are and how many of them fall outside of the well-defined categories that were laid out by Ide et al. So this is a plot that I made with Ashley Griffith for a 2015 paper, where we're like, okay, the interesting things about earthquakes, the things that are supposed to set earthquakes apart from any other creep or slip that happens in the Earth, are two things. So one is the slip velocity, and the other one is the rupture velocity. So I think Yajing probably went through how those things are different. I'm looking. Yeah, okay. Indistinct mumbles from the class, so I'm just going to go ahead and define it real quick. So the slip velocity is, if you're like a mineral grain in the rock on one side of the fault, it's the velocity at which you move past the other side of the fault. So that's how fast the rocks are actually moving. The rupture velocity is the velocity at which the area of rock which is moving is growing. So I like to think of it like if you're in a stadium watching a football game, sometimes you do this thing called the wave. And the wave is when people pop out of their seats and like wave their arms. And then once somebody next to you does it on your right, then you do it and the person on your left does it. So it's passed around the stadium. So if you are the little mineral in the rock, then the slip velocity is the rate at which you are moving when you do this. But the rupture velocity is the velocity at which the front of the wave is moving around the stadium. Does that make sense? Queens, you're the only people I can see. Can you wave if that makes sense? Makes sense to like two of you. Okay, super, I'm moving on. So both of these things are distinct for earthquakes. They're really fast. And the rupture velocity for an earthquake is the rate at which the tip of the earthquake is propagating along the fault is on the order of several kilometers per second. So that's much faster than we think than a creep event. So what this plot kind of shows, we have rupture velocity space on the y-axis, and we have slip rate space on the x-axis. And in the upper half of the plot, we have things that we observe in the earth. We have aseismic creep that's way down in the lower left corner. It has the green bar there, and that's showing basically negligible rupture velocity and slow creep rates. So this something like 10 to the minus 10, 10 to the minus 12 meters per second. Then we have intermediate events that are shown by these blue dots, and those cover slow slip events, after slip during earthquakes, things that are kind of in that middle range. And then earthquakes are in the red, and they're way up on the upper right-hand corner of the plot because they have very fast rupture velocity and very fast slip velocity compared to all other events. So that's what's shown in sort of the upper box of the plot. And then attached to both axes, I have these little extra boxes because in laboratory experiments for earthquakes, there are almost no there are no laboratory setups where we can capture both rupture velocity and slip velocity. And part of that is because the rupture velocity is so fast that if you have a little tiny 1-inch rock core, you can't really watch it rupture in real time. It's too fast. So, but there are ways to kind of get around this. So on that, there's like a little rectangle hanging off the right side of the upper part of the plot that is signatures of fast rupture that have shown up in laboratory experiments. And these laboratory experiments have like a different geometry than regular friction experiments, and I'll show you one example of those. But they do produce interesting deformation patterns, and so the two that we're going to talk about today is periodic cracking along the faults. That is something that happens at the rupture tip as a result of very high stress at the rupture tip. And the pulverization of rock, which can happen in big areas around the faults where the rock just basically explodes because of the high stress at the rupture tip. So I'll show you examples of both of those. Okay, down in the lower half of the plot is an area that's plotted only in slip rate without any rupture velocity because it's things that we do in the lab. So when you're driving your slip with a motor, it doesn't really make sense to talk about rupture velocity because it all depends on your motor, but not on your rock properties. And down here, we have a lot of the things that have been produced in laboratory experiments on high slip rates. We talked about some of these last week, pseudotacholites being the one that you're working on for your lab. There's also other kind of mineral reactions that take place at fast slip. Most of them are driven by the heat, the frictional heat that's produced during fast slip. Okay, so, well, this is the mathiest slide I have here, and I'm not going to go through what the math means, but this is an explanation for why there are really high stresses, or an explanation that there are really high stresses at the tip of an earthquake rupture. So if you turn your attention to the rainbow plots on the bottom row, what this is sort of like a box. Let's imagine it's a perfectly elastic rock. And there's a fault propagating into it from Y into the center of the box. And the stress anomaly caused by slip on the fault is colored. So the greater the stress anomaly, the darker the colors get. And for red, it's going to be compressional. And for blue, it's tensile stress. So if you had an elastic blob or a fault breaking into it, this is how much basically stress or elastic strain you would get in your rubber rock, whatever it is, your elastic rock. Oops. So on the left, we have the case where the propagation of this rupture into the elastic rock is going at 20% of the shear wave speed. The shear wave speed in rock is about 3,000 meters per second, 3 kilometers per second. I'm looking at the seismologist. He's giving me just a, yeah, okay. In the range, yeah. Okay, all right, 3,000 kilometers per second. So this is propagating at 20% of that, which is less than what happens in a regular earthquake. And on the right, we have the case where the earthquake is propagating, the rupture is propagating faster. It's reaching 80% of the shear wave speed, which is more typical for what we see for earthquake propagation. And you can see the magnitude of the stresses have really increased. We've got like a dark red patch now and very dark blue underneath the fault. So, and that the little dashes covering the area, the little black bars, are showing the orientation of the stress. So the other little subtle pattern that you see here is if you look at the left-hand plot where it's only 20% of shear wave speed, the little black bars in the light blue area where the tensile stress is are at an angle to the fault of about maybe 70 degrees. And then if you look at the other plot where you have very dark blue, so much higher tensile stresses, those little black bars have rotated so they're closer to perpendicular to the fault, over 80 degrees or maybe 90 degrees to the fault. So that's where, because rocks are stronger in compression and weaker in tension, that's where we have our greatest magnitude of tensile stress, and sigma 1 is at a high angle to the fault. So that would be a great place to look for fracturing that was characteristic of a very fast rupture velocity. And in fact, these experiments have been done. This is some experiments by Ashley Griffith, who's my co-author on the other paper. So this is not a rock. This is a plastic block, birefringent plastic block. What they did was cut a fault into it, basically put a saw cut through it, glue it together so it would have some non-zero cohesion, strain it so that there was some differential stress that would favor slip on the fault, and then the little wires that look like a dark arrow that are pointing to the fault zone, that's an electrode. So they set off a little tiny charge in the fault that started the glue from breaking, and then it broke down the fault and would cut through all the glue, like an earthquake rupture, propagating through a fault, a planar fault in a cohesive crust. So the reason why they use plastic instead of a rock, of course, is because you can shine light through it, and it's birefringent. So all the fringes that you see in there actually represent the pattern of stress in the plastic around the fault as the fault is rupturing. It's a pretty cool thing to be able to image. So he's got, as you go through the panels here, it's like a cartoon of his experiment from 50 microseconds after rupture to 80 to 105. And what you can see there is that, like, if the stress fringes are forming a little flower on the fault, the center of the flower is where the tip of the rupture is. So there's stress on both sides of the fault around that rupture, and the stress anomaly around the fault is following along with the tip of the rupture. And you see on what would be the left side of the fault, there's kind of a shadow that forms that's permanent damage in the slip zone. So if you take those plastic blocks apart after the experiment, you see that all along the fault on the tensile side, you have these very tiny tension cracks that have grown. They're at a really close interval, and they follow that blue patch, that tensile stress anomaly behind the rupture all the way down the fault. And so Ashley wasn't the first one to notice this, but he did document it really elegantly, that it has a lot in common with the patterns of pseudotacholite injection veins that we see along natural fault surfaces. So I just wanted to put in one example of that from our field work. This is actually from Catherine's. Oh, she's not here. Catherine's field area in Fort Foster in the Norumbega Fault Zone. So these are beautiful mylonites that are formed in amphibolite facies, metamorphic rocks. And you can see running through from the little coin on the left side of the left edge of the photo, you can see that there's a sharp slip surface going across the bottom of the screen. And you can see that sharp slip surface because the myelinitic foliation is at two different angles on either side of it. And regularly emanating from that sharp slip surface, but only to what's the upper side, so toward the top of the photo, are little brown and gray fingers of pseudotacholite, little injection veins. Some are quite tall, like the one in the middle of the screen. Some are quite short, but they're spaced only about a centimeter or two apart. And this is a really common observation that we see in pseudotacholite bearing faults, and we think this is really well explained by the homolite experiments that show these regularly spaced but variable height cracks forming in the tensile side of the rupture. So from this, we can interpret in the rock record not only that an earthquake has occurred, but we know which way that fault was rupturing, which is a pretty exciting detail. So depending on the confinement, the rock properties, maybe what water is present, other things that we don't even know how to define yet, that same stress anomaly that migrates along with the tip of the rupture can cause even greater degrees of damage. So this is an example of a similarly small fault. We estimate these are like 4 or 5 magnitude earthquakes, where the one wall of the fault is just completely exploded. So forget your little tensile cracks. Now you've got a million tensile cracks instead of a few nicely spaced ones, turning that myelinite completely into a breccia. This is only a few centimeters thick, but here's an example of is it going to switch? Oh, we're stuck. Okay. Here's an example of a photomicrograph of one from the southern San Andreas fault. And when this effect takes place near the surface, where the rocks are less confined, and in very rigid rocks like granites, like this one is, there are so many tensile fractures that form in such a short period of time that the rock is basically exploded in place. So this is known as pulverized rock. Some people don't believe in it. Some people think it's just weathered rock at the surface. But the people who documented this showed that if you zoom out on a larger scale, this rock basically still has its primary igneous texture of a granite, but all of the grains are broken on the sort of 10 micron scale, but none of the grains are displaced. So really, really high fracture density without weathering or displacement along the fractures, which is hard to explain by any other mechanism except for kind of co-seismic pulverization. So this is something that was only discovered a few years ago. Since it was discovered on the San Andreas, there have been examples that have come up in Japan and Turkey and a couple of other places. And what people are doing to investigate this, which I've only seen reported at AGU and I haven't even seen it published, but they're taking little cores of different rock types that you would find along a fault, and they're putting them in some kind of high pressure bomb. And they've had to contract the military contractors that work with the US government in order to find the bombs at high enough pressure that will vent fast enough. So they take them up to extremely high pressure inside the bomb, and then they just let it go. They just vent it really suddenly. So it would be equivalent to a contractional pulse and then a really sudden tensile pulse. And from these preliminary set of experiments, they did about 10 different rock types, and about 5 of them went to dust, like this photomicrograph. And the other ones maybe had 1 crack or 3 cracks. So they're still trying to figure out why different rocks reacted differently, or if the depressurization rate is more important, or if it matters if they've pressurized them in an air medium or in a water medium and all of this kind of stuff. So hopefully we're going to see some publications come out from that sometime soon to understand how pulverized rock works. This is probably an important mechanism also for crustal deformation and impacts, by the way. So interesting to think about. So I think that wraps up what I'm going to say about fault slip rates today. We covered most of the fast slip stuff last week with some examples of that. So you can go back and look at those slides if you want to see what those kind of rocks will look like. And now I'm going to move into talking about subduction faults. Are there any questions before I do that? I'm going to take absolute silence as a no. Move on. All right. Okay, so subduction thrust systems have a lot in common with fold and thrust systems that form in continental environments, except that you can sail over them in a boat, which means that you can image and produce cross sections of the whole thing, which is kind of fantastic. This was published in 1990, so this data was collected sometime in the very late 80s in Nankai Trough. So this is southwest Japan. It's the same subduction zone that we talked a little bit about last week, because it has, it's very well studied. It's been a focus site of the International Ocean Discovery Program for many, many years. So there's a lot of good data on it. And so if you look at the top and the bottom plots of this seismic line are the same. The bottom one just has the interpretation drawn on it. So overall, you can see that you have, if you start at the top and look at the far right, the kind of light gray stuff is water. And then you get to the seafloor is shown with basically a sharp, dark line. And everything beneath that's in like the high contrast colors is the subsurface. And you can see the first order thing to see is that you have a few kilometers in the subsurface of well stratified material, which is sediments. And then you get kind of a fuzzier material beneath that. That's basaltic crust. So that is the subducting oceanic crust. And if you look to the right, you're looking out toward the ocean, and the left is toward the land. So on the right, you're looking at the oceanic plate that's coming in toward Japan, which is the Philippine Sea Plate, and subducting to the left. And what we're looking at here, and why this area was targeted for the seismic investigation, is this is basically the toe of the accretionary wedge. This is where the deformation starts. Once you start with this nice layer cake geology on the seafloor, and as it comes in and starts to collide with the overriding plate, you see the beginnings of deformation and the structural development of the accretionary wedge. So on the lower panel, they've labeled a few things here. DSDP stands for Deep Sea Drilling Project. That was the first name for the international consortium of governments that share science boats. Now it's called the IODP, International Ocean Discovery Program. And then so 582 is the 582nd hole that was drilled by DSDP. So that was out there on the incoming sediments, and the reason why you do that when there's no deformation is to find out what your sedimentary layers are. You know that the ones that are coming in may or may not be the same as the ones that have already been deformed, but it gives you a reference section basically for doing seismic interpretation or structural interpretation. Then moving landward, we hit the deformation front. So this is the first place where that incoming sedimentary section where you start to see at least seismically resolvable evidence of structural deformation occurring in the sediments. And that shows up in the form of sort of little wiggles where the planar stratigraphy starts to be non-planar. But out here, it's still kind of diffuse and distributed deformation. As you move farther landward, we enter the proto-thrust zone. So this is where you start to see that there's real steeply dipping toward the landward direction. You can see that there's some patterns showing up there in the seismic, and the irregularities in the stratigraphy are starting to resolve themselves into faults and folds. You can also see, if you look directly beneath the words proto-thrust zone, that this deformation is only affecting the upper part of the section. At the very base of the sedimentary section, right above the oceanic crust, the sediments are still flat-lying and smooth. Interesting thing to note. And then as we continue to move to the left, there's first thrust is marked, where the first time that you see a thrust actually break the surface of the seafloor. Just to the right of that, there's actually a little thrust that's marked on the section, but it doesn't have a label. So it looks like that's a blind thrust. It's deforming, it's cutting the strata at depth, but the strata at the seafloor are forming an anticline over it, so that the thrust hasn't propagated all the way through yet, but it will. That anticline is marking the propagation of that thrust toward the seafloor. And continuing left, you can see that behind first thrust, there's actually another flat-lying section of sediment there, and some really messed up sediment where you can barely see the stratigraphy anymore underneath that little triangle of flat-lying sediment. So that means, in terms of the seismic line, that whatever the density of structures is there, the complexity of faults and folds, they may be at a smaller scale than the seismic waves can actually image. And then you get this seismic blanking where everything just looks a mess. It looks like noise on the old black and white TV, because if the seismic waves, you can usually get a good image for a feature that is about all the way down to about half of the wavelength of the seismic waves, and anything smaller than that turns into scattering and noise. So we're getting more structural complexity, we get more scattering. We also have a funny thing show up there. You can see the little note that says gas hydrate. If you look at that same spot on the upper section that's not all marked up, you can see that there's almost a zone along the seafloor. There's something called a bottom simulating reflector. There's a dark line that is spaced below the seafloor at a regular interval and kind of copies the bathymetry on the seafloor. So that extends from the word gas basically all the way to the edge of the section. You can see a little line there. So a gas hydrate line is where methane is trapped in the form of hydrates, so basically like methane water, snow looking stuff in the pore spaces of the sediment. So it's seismically resolvable because it has a different velocity than the normal rock, so there's an impedance contrast there at the bottom of it. And it's important because it can trap methane or other fluids that are coming up from depth in this fault system and trap them below the seafloor there. So if you were in the business of ocean drilling, seeing a bottom simulating reflector like this is basically your worst nightmare, because it means you're going to have pressurized pockets underneath that layer. If you penetrate that, you might have a blowout. Pretty exciting. So here's just two examples. That's the Nankai Trough again on the top. It's Barbados on the bottom, where people have started to pick apart the kind of the structural indications they're seeing in there and look at the difference between different fault systems. So on Nankai, we have big splay thrusts coming up from the décollement zone. And we have a sharp distinction between deformed sediments and the trench fill sediments that are effectively undeformed. And then in Barbados, the structural evolution has proceeded differently. Instead of having like a big duplex system with a bunch of splay thrusts, we have distributed deformation, and then at the floor of that we have a single sort of ramp flat anticline that's going up toward the ocean surface. So although these are very similar margins in some ways, their structural evolution has gone very differently. So this is a paper by Fisher and Byrne in 1987, and these two guys were rummaging around in the Kodiak accretionary complex, which is a Mesozoic age accretionary wedge that's basically all of southern coastal Alaska and continues almost around the orocline a little bit into BC. And they were able to distinguish, even though this is old and preserved on land and it's probably been subsequently deformed, that there were kind of two classes of deformation that they saw in the sediments here. And so they divided these into off-scraped sediments and under-thrusted sediments. And that was inspired in part by this observation from the seismic lines that you can have from the right-hand side of the diagram where you have flat-lying sediments that if you go underneath the accretionary wedge, underneath where the major slip zone is developing, you're still going to have flat-lying sediments that go down that can propagate pretty far to the left in these subduction zones. So there's a division between the upper part and the lower part of the incoming sedimentary section that results in a different structural evolution for those two groups of sediments. So in the upper part, we have off-scraped sediments. So this is kind of your snowplow situation where these things come in and then they basically get scraped off by contact with the upper plate, and they end up with big upright folds and not very deep burial. And they're divided by this fault zone from under-thrusted sediments, which are getting successively buried and actually really quickly buried because of the increase in the topography on the seafloor. They're actually getting buried because they're tectonically moved under thicker and thicker sedimentary accumulation. So these bottom two pictures here kind of show what deformation is happening along that fault during that time. On the left-hand side, we have a photomicrograph that shows like a little sandstone blob with a shaly and sandy matrix around it. And you can see that although these things are at really low temperature, what we're seeing is macroscopic ductile deformation by the mechanisms of cataclastic flow, solution creep, and particulate flow that are resulting in this sort of ductile deformation, but none of it is crystal plastic. And to the right, we have the next stage of that deformation. So once that macroscopically ductile deformation has started to stretch out all of the sands and shales and take the subducting sediment and kind of mix it like that, it's actually, because it's being buried so fast, it starts to lithify, just like a sediment that was going to be buried in a basin or something. So as it gets harder, it starts to favor the development of discrete faults. And so here's kind of a intermediate stage where these discrete faults have started to develop, and you can see that there's really fine displacements of, on the orders of tens or hundreds of microns across these little faults. And if this were allowed to continue, eventually some of these would take over and grow into big faults, and then you would have a rock with faults in it instead of flowing sediment. So there's an incremental transition that goes on in this environment. So here's Fisher and Byrne's kind of diagram of how that works, and obviously these are sketched from the exact micro photographs that they put in the paper. But the first stage of deformation is this kind of distributed disaggregation, and then you have sequential localization where you start with shear bands that are a few grains thick that form in stage 2. By stage 3, these have moved on to become discrete faults in their own right, and but there's still a network of faults, and they're moving toward the direction of having a single, more mature fault. Meanwhile, the sediments that are going under it are just being flattened. So all that they experience is some layer parallel extension and some layer normal flattening. So when you find these in the geologic record, in fact, they look quite different, and you can easily structurally distinguish which history the rock has been through. So also, the other thing that's going on in this environment, which was alluded to when we saw the gas hydrates, is a ton of fluid flow. So the first stage for all these sediments, no matter what happens to them, is the compaction and the expulsion of pore water. And so even as early as the frontal thrust out there, there's a couple of little asterisks that are shown on little splay faults at the frontal thrust. Those are showing where pore water from compaction of sediments can be vented up to the seafloor. So there's cold seeps on the seafloor. In general, the water that's coming out there is not so different than the seafloor water, although it might be a little bit warmer because it's coming from depth. And even a little bit warmer than 4 degrees is enough oftentimes to have those vents colonized by organisms. Then as we move back in the prism here, the farther the sediments go down, if the sediments have any kind of organic material in them, which they usually do, that organic material will start to mature. And so a big source of fluid coming out of the sediments is actually the early production of oil and gas, or hydrocarbon liquids that come out from the maturation of sediments. And that can start to produce, well, CO2 venting, methane venting, or even oil venting to the seafloor. And obviously it depends on the local thermal regime, at what depth that will happen, and it depends on how much organic content is in those sediments. It also depends on how much, what else does it depend on? Yeah, it depends on all those things. So, and then the hanging wall and the footwall sediments often, because they're being compacted, they lose pore space and they start to become less permeable. Now that becomes really important because the 2 ingredients, that we'll come back to this at the end, the 2 ingredients for high pore pressure are low permeability and fluid supply. So it doesn't matter how much fluid is produced out of the sediments if your rock is a big open sponge and it can all vent to the seafloor, then it basically has no mechanical effect. But if the sediments are getting denser and the pore spaces are getting less connected, then the fluids can be trapped and generate high pore pressures. So here on this diagram, we have this big black tube with white arrows that's extending from the underthrust sediments up to the seafloor where it produces a mud volcano. And so these are places where the fluids were at higher pressure because they were deeper. And if they find a pathway, in this case, one of these splay thrusts to vent to the surface, they're going to be accelerated by that pressure drop as they flow along, and they're picking up sediment along the way. So they can vent to the seafloor. And a great place to look at this would be in the Marianas Trench, where the fluids that are coming up on these pressure gradients are coming from so deep that they contain blue schist dust. And there are blue schist mud volcanoes growing on the inner trench slope in the Marianas Trench, which is just amazing. Sometimes there's like large blue schist rocks that come up with them. That's how much energy that they actually have. Okay, so this is what I spent most of the weekend drawing. This is my compendium of what an accretionary wedge looks like. So I hope you'll enjoy this drawing. So it's just a cartoon that's compiled from the other cartoons. But these are kind of since we're in a class called Anatomy of Fault Zones, I thought I'd show you the anatomy of the accretionary wedge. So from the outer, we'll start at the right where we have the incoming plate. It has some layer of sediments on it of some thickness. The outer rise is the area where the plate bends to start descending into the subduction zone. And because it has some rigidity to it, there's actually a little elastic sort of bump that forms there, which is called the outer rise. And because it's a little bit of a fold in the plate, you can actually get a little extension around the surface of the outer rise. And normal faults are often active there. And they don't have a huge amount of throw. It could only be 100 meters or a couple hundred meters. But it's often enough to offset the incoming section And it creates some topography on the seafloor that can play a big role in interacting with the upper plate later on. And the other thing that it can do is tap fluid sources beneath the sediments. Sediments are a great seal on the seafloor. The basalt beneath them tends to be higher permeability. And if these faults break all the way down to the mantle, it's possible actually that they could either play a role in bringing water down to hydrate the mantle of the downgoing plate, or to tap water sources from hydrated minerals that are already down in the lower crust that may have formed by hydrothermal alteration at the mid-ocean ridge when the crust was first formed. The point of intersection between the two plates at the seafloor, or otherwise known as the place where the plate boundary thrust actually meets the sea, is called the trench. It's usually the deepest parts of the ocean are subduction trenches. The deepest is 10, and some of them can be actually quite shallow if the plate is subducting at a shallow dip. Then there's a couple of basins where sediments are deposited on top of the accretionary wedge. Most of these sediments are going to be sourced from the volcanic arc, which is off this diagram to the left. But the first one is the trench slope basin, which I've kind of drawn in here, and you can see there's an unconformity with some sediments lying on top of it. And those sediments are derived either directly from the arc, or they can erode off this forearc high. And oftentimes in the trench basin, you have really beautiful canyon and distributary channel systems developed that bring sediments down to the trench. So you can accumulate sediments in some parts of the trench slope, and other places are actually eroding and draining sediments down into the trench. But both of these contribute to the amount of sediment that actually goes down to the trench and may subduct in the end. Underneath that unconformity, we have variably deformed units of previously accreted sediments. So these are sediments that came in and either off-scraped or underplated in the accretionary wedge. And I've drawn off-scraped units into the lowermost one of these fault-bounded wedges. And the characteristic structural style, like Fisher and Burns showed for the off-scrape material, is horizontal shortening. So oftentimes it's characterized by upright folds. Vertical solution cleavages are common. And especially in the limbs of folds, we see a lot of extension of the bedding. It's kind of bedding parallel stretching by those same mechanisms we talked about: cataclastic flow, particulate flow, and solution creep. So that might happen right at the trench. And then as we go down, the forearc high is often produced actually by throw on these splay faults. So in this case, I didn't put a little arrow on it, but there's a thrust fault that daylights to the ocean right under the word high of forearc high. And so this one, if it has throw on it, and you can see it's dragging the sediments there consistent with thrust motion, that would elevate the forearc high, which contributes to producing some topographic relief that impounds the forearc basin and also acts as a sediment source for the trench slope basin. So the forearc basin is a little bit of a apparent paradox, because why in this big plate collision zone do we have all these normal faults, and why are they forming an extensional basin? And the reason has to do mostly with what the dynamics are below it on the slab, which I'll get to in a second. But the forearc basin is a pretty common phenomenon, and it's a pretty major part of the sedimentary record of subduction. It's also the water depth is less, so it's more accommodating for the biology potentially, because these normal faults can also be bringing up those fluids from below that will support chemosynthetic communities if given the chance. Underneath the forearc basin, we have some back part of the wedge. It could be formed of old accreted sediments, previously accreted sediments. It could be formed of whatever the leading edge of the overriding plate was before the subduction developed. And in fact, if you continue kind of to the left of the photo, I just stopped drawing stuff in there, because what happens there is you get rocks that are hard enough and lithified enough, metamorphic rocks or crystalline rocks, that seismically you can't necessarily distinguish by their character whether they are old continental crust forming a backstop to the system, or if they are metamorphosed accretionary wedge sediments that basically have the same mechanical properties and are forming a mechanical backstop to the system. And in fact, it's different in every margin, what the history is and how it got set up. So the kind of, well, okay, my favorite part of this whole system is down at the very bottom here where I've marked underplated units. So the base of the accretionary wedge. This is where packages of sediment, just like the sediment that's subducting in this picture, have come down, got deformed, and then for one reason or another, the plate boundary fault, which was on top of those sediments are riding down with the subducting plate, the plate boundary fault cuts down into those sediments or into the subducting crust itself and basically migrates down, leaving abandoned the old plate boundary fault, which can be marked by this sort of continuous line across there on top of the duplex, and abandoning that package of sediment at whatever metamorphic conditions are there. So this is the accretionary wedge growing from the bottom, and this process is called underplating. And most of the volume of sediments in most of the world's accretionary complexes are added in this way. And this is why they are subject to this low-grade metamorphism first. That's why we have blue schists, green schists, and eclogites in accretionary wedges, because they do go down quite a ways. And then when that fault system migrates, they are abandoned there. So I put some colors on here to kind of represent what those different metamorphic facies would be and what you would see if you were lucky enough to find an outcrop that exposed a cross-section through this wedge. So those underplated units I just referred to, I put in blue with a temperature of maybe 325. Those would be where units had subducted into the blue schist facies, which for the sediments usually means they just grow a little bit of jadeite. They're not like real nice crystalline metamorphic rocks because the temperature is too low to have a lot of new mineral growth. And then they get abandoned there. But those thrusts are still moving. So above the blue schist, we see green schist facies rocks, which have marked at about 225. So for most of these sediments, that means like maybe a bit of chlorite, maybe some, maybe some epidote, mostly chlorite. And the yellow color at 125 would represent sort of prehnite pumpellyite facies in the sediments. And depending on how much lithic material you have in your sediments, you probably have either prehnite or pumpellyite, maybe both. And what else? Yeah. So if you can see that the colors are kind of offset, if you look at the little slab of downgoing sediments that are still subducting with the oceanic plate. And that's because they're starting to go through these different metamorphic conditions as they migrate down. They're starting to lithify and turn into rocks and metamorphose. But the action of the thrust might bring the blue schists up higher. It might bring the green schist down lower beneath it. But it normally produces this typical pattern where we have the action on the thrust causes an inverted metamorphic gradient. So a higher metamorphic grade in the blue stuff in the hanging wall, lower metamorphic grade in the green stuff in the footwall. And this is one of the things that we use to find these thrusts in the rock record, to find them when we're looking at an old accretionary wedge complex, is where we have an inversion, usually in depth. So we count on pressure more than temperature. So in the Franciscan complex where I'm currently working, we can find, there's a number of faults that have jadeite, lawsonite bearing sediments, which would be the blue sort of hanging wall, over prehnite pumpellyite bearing sediments, which would be the yellow. So this is telling us that we had a subduction thrust that was active at one time that has a throw on it in the ballpark of 10 to 15 kilometers. That's just the vertical displacement kind of suggested by the metamorphic grade. So 10 to 15 kilometers of vertical motion on a fault that probably dipped 10 or 20 degrees is 100 kilometers of offset. So 100 kilometers of offset on a subduction system that maybe goes at 10 centimeters per year gives you an idea of how long that fault was active for. It also gives you an idea of how many great earthquakes it might have had, which is kind of a fun, it's a back of the envelope thing to play with. Like you have a hard time putting that in the paper if you don't know exactly what the rates were, but it's a neat way of thinking about it. The subduction of the sediments being at lower grade than their hanging walls also means a couple of interesting things. One is that all of the fluid sources that come from those sediments or from the crust beneath them, they're delayed with respect to where their hanging wall is. So I've got the sediments that are still white, I've got marked as kind of diagenesis. So that's compaction and the early stages of generating fluids. and the yellow sediments were generating a lot of fluids. But those yellow sediments and even the green ones are extending underneath what are moving toward being crystalline metamorphic rocks. So that's an ideal kind of condition for you have sediments, you have water or fluid supply from below, and you have compaction and increasing density and reduced permeability above. So that's the kind of condition where you would see elevated pore pressure in the fault zone. So we've got little blue arrows on here to show where some of the fluid sources are. We have diagenesis in the upper part. We have fluids that have made their way and coming out the Forearc Basin. And then there's a couple of little blue arrows that are way down in the oceanic crust to the lower corner of the diagram. And that's showing where some of the mineral bound water in the oceanic crust starts to come off. So this is where if you've produced, say, oceanic crust contains a lot of alteration, hydrous alteration minerals that are formed during the time that the crust is formed, and those start to destabilize at a certain temperature. And so you get mineral water, which is fresh, metamorphic fluids coming up and entering the fault system there. So whatever reaches the surface is a mixture of all these sediment sources and depends on the structural evolution of these faults to find its pathways. Yeah, so.
Christie?
Yeah.
I've got a quick question. If you go back to your previous sketch there,
yeah.
And you may come back later on to this. In your wedge there, in your schematic diagram, you have a vertical zonation in the style of deformation whereby in the underplating zone, it's mostly compressional features and thrust faults. And
yeah.
As you move the shallower part of the wedge, it's actually an extensional style of deformation with normal faults that's causing I guess, the basin or the room to accommodate the formation of the Forearc Basin.
That's right.
Could you explain how you go in that same wedge from compressional deformation at depth to extensional deformation in the shallower part in the same wedge?
Yeah, well, there's, depending on the specific case you're looking at, there's different explanations that are possible. Because the one thing about this whole construction takes place over an extended period of time. And in fact, it looks like any individual accretionary wedge will go through stages of really voluminous accretion. Like if you have like in California history, for example, in the late Cretaceous, the Sierran Arc was super active. There was a massive pulse of sediment supply into the Franciscan Trench. And so during that time, a lot of sediment off-scraped and a lot of sediment subducted and underplated. So during that time, the wedge was thickening and elongating at the same time. Immediately after that, and actually immediately before it, there was the trench was almost starved. So there was a lack of sediment coming into the trench. And so during that time, the wedge found itself over-steepened and went into collapse. And so we developed the whole Great Valley in California, which is this big Forearc Basin. So that's one of the dynamics that you can play with that can change the regime of the wedge. Another one is the dip of the slab. So the dip of the slab is controlled by the convergence rate, the density profile of the slab, the direction of convergence, so how much of the plate motion is actually directed into convergence. And any small variations in those can change the wedge dynamics and throw the wedge from collision into extension. So the profile I drew is kind of based on a composite of lots of different wedges, but it doesn't necessarily mean all these features are active at the same time. But in fact, now I'm thinking about Nankai does have all these features active at the same time. So another explanation that's been thrown out there, which I'm not a huge fan of, but some people are, is that there's an additional regime for the wedge would be a time when those rocks at the bottom, those 325 blue rocks right there, might actually rejoin the lower plate. So if the fault moves back up through the section, then they would call that tectonic erosion, where that material gets scraped off by the downgoing plate and then rejoins the downgoing plate. And conditions that might cause that would be things like subduction of a seamount or an oceanic plateau, something that can act like a buzzsaw and tear away at the bottom of the accretionary wedge to remove material. So if you remove material there, then you would expect that accretionary wedge to go into subsidence, and then the phoric basin would develop over the removed material. So those are some of the mechanisms that might cause it. I'm sure there's others as well.
Okay, thank you, Chris.
Yeah. Okay, so here's a little diagram that shows everything I just showed you is in the upper right in that yellow accretionary prism area. So this is extending it all the way out toward the overriding plate to the volcanic front there, so that you can see the arc on the surface there. There's some kind of arcuate feature in the edge of the magmatic arc crust. I don't know what that is. Maybe that's based on something specific. But this is showing going all the way down from, I just got to the start of a blue schist zone, and this is carrying it down through blue schist and into eclogite metamorphism. So, yeah, they have an excessive number of wiggly arrows showing like where water would come out of the crust. That's based on metamorphic dehydration reactions. And they've also got an interesting thing going on where this light green color in both the overriding and the downgoing plate represents mantle material. So that's peridotite. And when you have all this water coming out of the slab and going into the peridotite, it produces serpentine. And that reaction, serpentine is way less dense than peridotite. And it's also viscous at most of these conditions with a very low viscosity. So it can flow through the structures. And so what this diagram is actually exploring here is the idea that the water in the downgoing plate coming out and reaching the mantle of the overriding plate, producing a big body of serpentine that's shown in this purple kind of patterning here. And as it does so, maybe it's picking up blocks of this metamorphic rock that's coming from the downgoing plate and starts to carry that up and squeeze it up some of these structures toward the upper crust. And you can see this, there's like a little finger of purple material that's kind of trying to creep up one of the splay faults toward the trench here. And this might sound kind of outrageous. It does sound kind of outrageous, but in fact, in a lot of accretionary prisms, we have serpentinite matrix melanges, and sometimes they contain high-grade metabasite blocks, eclogite blocks, blue schist blocks, things that could only be mixed together in an environment like this cartoon shows, and how they creep up and end up between, along faults and in layers within the sediment of the accretionary wedge is still a matter of a lot of debate. So they're pretty common in California, but some people think that they came up later on the San Andreas fault, or that they were basically brought to the surface by splay faults like the ones coming up to this 4-arc high, and then subducted basically as sediments down into the trench, and so that you have some kind of mixing that goes on in the accretionary prism environment because of the exhumation along thrust faults and then the subduction once they reach the trench again. Yeah, so that's sort of a case-specific area where you have to look at the architecture of the whole system and figure out what a reasonable mechanism of exhumation of these deep-seated rocks might be. But this is sort of the system of circulation that's thought to create them and bring them to the surface. So to finish up talking about subduction, I just wanted to go through a quick example of a field area where we're looking at this. And if I could just go back to if you look, forget about the grade for a sec, but if you look at the blue schist blocks where I've got the underplating, you'll see that it's like a duplex structure. There's a roof thrust and a floor thrust and a whole bunch of imbricate thrusts in between, and each one is bounding a package of sediment, which might all be similar to one another, but they're separated by individual thrusts, so little imbricate sediments. And this is an example of one place where we think this happened. It's called the Marin Headlands terrain. It's in California. It's part of the Franciscan complex, so it's Mesozoic in age. And this map shows repeating thrust imbricates of greenstone or basalt, which is green, chert, which is like maroon colored, and trench sediment, which is blue. So we think that these are basically the components of the downgoing oceanic plate. We have more chert overlying that, which would have been the pelagic chemical sediment. And then we have the trench sediments. So that would have been added to the plate as we got near the trench. And this was identified by the great Californian geologist Clyde Warhoftig in 1984. And he used to take his intro mapping classes here, which I think is not very fair because all of the units are the same. They repeat 17 times. The exposure is not that terrific, but it's a really gorgeous place to walk around. You're right over the Golden Gate Bridge. The scenery is very nice. But like I said, the outcrop is not great. It was heavily grazed in the 60s, and there's like soil and grass over everything. So what we did, I went out with a postdoc, Christine Regala, who's now a professor at Boston University, and they just remodeled these roads out here, basically Alexander Road, which is down near the lower right corner near the Golden Gate Bridge, and cut a bunch of really big new road cuts that are continuous for several kilometers. So we were able to go back, and instead of piecing together from little bits of outcrop in the grass what the lithologic banding was, we were actually able to go and look at the imbricate bounding thrust faults individually. So here's the map we made. It's not huge, but it crosses a couple of imbricate thrusts. There's big sections of chert in there, some repeated sections of chert, which is in red. There's the greenstone basalt, which is in green, and then we have white chert, which is in like a beige color, and then we have the dark brown is clastic sediments. Oops. Yeah. So because we know the order that these rocks would have been in the incoming plate, we know the basalt's at the bottom and the clastic sediments are at the top. So as we're going through and we find the individual faults, we can determine when we've crossed from one imbricate into another. And here's an example of basalt, which has been thrust over a shale greywacke kind of melange, stratified sediment. So we know this is one of the imbricate bounding faults that's displaced the entire section and put the base of the section on top of the section, effectively. And there's Christine taking some notes like a good field geologist. We also found as we went through, between the faults, through one sedimentary package and into another. I don't know why this is taking a minute to change. I'll just be patient and not try to press the button. There we go. This is some of the chert layers, and the cherts are really beautiful because they're radiolarian cherts, and they're ribbon cherts, which means that every couple of centimeters they have a tiny thin layer of shale that was deposited there. So it breaks up the cherts, but it also makes this like wonderful rheologically discontinuous material that loves to make chevron folds because it slips on the layers, on the little shale layers. And so looking at these folds, we've got the white dashed lines are outlining bedding planes. The yellow lines are faults, and the little blue dotted lines, if you can see them, those are the trace of fold hinges where they come out on the road cut there. So you can see if we start at the lower left, there's a fold hinge there that as you follow it up, it gets sharper and sharper, and pretty soon the fold hinge is actually broken and offset, and it becomes a fault, and it carries on up. So the top to the right shearing that produced that fold also produced that fault. And we consider those to be essentially one and the same, like a transitional structure. And we can say those are kinematically coupled to one another. They form during overall top to the right shearing. And the same thing happens down in the lower right part of the page, where we've actually got some faults that are in a normal geometry. That is that the hanging wall is moving down dip relative to the footwall, but they have the same sort of top to the right shearing sense, and they are often crust cut or folded by some of these other folds. So what we saw in these cherts is that same pattern of deformation that Fisher and Byrne were talking about for the underthrust sediments, where you have a strong sense of shear, subhorizontal shear, the parallel to the décollement, and that's giving us our top to the right shear sense. But we're also seeing, although those are thrust faults, we're seeing normal faults that are developing during the same shear because of all the flattening of the sediments that's going on as they get pressed down underneath the wedge. So here's another picture of a fault, what those faults look like in here. And here's our kind of transect across our field area where we have some steep thrust faults, some of which displace the whole section, some of which displace only part of the section. We have some steep faults in between them that seem to also be showing the same sense of vergence as the thrust faults. And we came out with a three-dimensional model that shows some of the complexity in the evolution of this fault system. So you can see that here we have 3 individual imbricates bounded by thrust faults. Each one has basalt at the base of it, so we know that that's where the fault cut down into the continental crust and basically abandoned that package of sediment. And each one of these is cut by high angle faults at different angles. Some of them have tight folds in between. Some of them are essentially undeformed in between, like the one between fault 1 and fault 2 has flat-lying sediment. So this is showing that this underplating thing happened repeatedly in time here. And since our spacing between these is a couple hundred meters, and we know from paleogeographic reconstructions what the convergence rate was in the Franciscan subduction in the Cretaceous, we're estimating that actually one of these new packages would have underplated every 10 to 100,000 years, which is really pretty frequent in terms of the reorganization of the wedge and how quickly it's going to change shape with this material added underneath it. So this represents a very specific period in time where thickening by this mechanism was favorable in this particular subduction zone, and so it stacked up a whole bunch of material from underneath. The other thing that the point we're trying to make in this paper is that if you don't take into account the strike and dip of all these structures, they're not parallel to each other. So if you took a single seismic line across this, you would not be able to make sense of the deformation. It would not be restorable because a lot of the slip is not pure dip slip. And so there is no single cross-section line that would actually be restorable and show you the true offsets through the system. You have to take into account the 3-dimensional geometry of it. Okay, so to sum up and kind of relate that back to the earthquake story, we have at the top of this diagram, this is a summary paper by Thornley in 2015. At the top of the diagram, we have this same kind of cross-section through a subduction zone that goes all the way down to the mantle and the overriding plate. So it's more like the Sujimori diagram than the one that I drew. But it shows how different parts of this plate interface system are exhibiting different types of deformation with respect to the earthquake cycle. So region A, at the very top, we have earthquakes that start at depth can rupture through up to the trench, but we don't have a lot of earthquakes actually nucleating up there. So we would actually say A is not part of the seismogenic zone. B is where we have large slip earthquakes. So that would be the seismogenic zone, strictly speaking, where most of the earthquakes are generated. C, we're getting a little deep. We're getting into the mantles. So like we talked about last week, you might be getting involved with serpentine forming in the upper plate there that could potentially lubricate and prevent large earthquakes from forming there. And then D, we start to get these other seismic signals of slow slip, episodic tremor like we have in Cascadia that we don't really understand the mechanism very well for. And then Thorne's drawn, or he's redrawn from the student Sue Billick actually, this cutaway diagram to kind of show what those sections A, B, C, and D would look like in terms of the conditions on the plate interface. So in the seismogenic zone, zone B, there are big red patches. Those represent locked patches on the fault that could potentially break and be earthquake rupture planes. Around that, we have these orange areas. So this is stuff that is not going to nucleate an earthquake on its own, and that's why it's conditionally stable. But if an earthquake nucleates in a red patch, it can propagate through an orange patch. And so he's got the orange patch up toward the trench is labeled as slow tsunami earthquake. And that's because an earthquake that nucleates in a red patch can rupture all the way up if it's big enough, has enough inertia. And if it upsets the seafloor at the trench, that's where we're going to get a big tsunami forming. And then the white zones on the plate interface theoretically are just aseismic. They're places that no matter how you push them, they're only going to creep quietly and not radiate any seismic waves. So in summary, the main points from this part, the footwall and the hanging wall and subduction thrusts are undergoing diagenesis and prograde metamorphism during the activity of the fault. So the conditions are changing in real time while the fault is active. The hanging wall has seen greater displacement than the footwall along the same fault. So nothing about the system is actually restorable, which is kind of a weird geometric phenomenon. Conditions along the fault change in the dip direction, sometimes in the strike direction as well. And that's temperature, pressure, mineralogy, rheology, and also the fluid conditions. And that whole system has big zones of conditional behavior, and like the orange zones on the last slide. And what that means is that they can rupture in an earthquake, but they can also creep aseismically, and it just depends on local tweaks. If you hit it with a rupture from somewhere else, if the pore pressure changes, they may fluctuate between being red-like or being white-like, depending on what the local conditions are. So, and we don't have a very detailed map of what those look like, whether they're persistent in time, which would imply that there's like a geologic driver, or whether they change all the time, which might mean it has to do with the local pore fluids. So I think, yeah, that's the end of this section. Should we take like a 10-minute break?
Yep.
Yep, okay. So I have 2:41. You want 10 or 15 minutes?
10 minutes, good.
Okay, let's start again at 2:51. Thank you.
All right, thanks for sitting.
It feels weird lecturing with my back to you guys. Yes, I can turn around. It feels weird using my inside voice when my outside voice when there's like 4 people.
Shouting to a screen.
Yeah. Is that clear?
Yeah, so. I thought one of the other reasons you can get like extension in the shallow part of the wedge, so it's like critical taper angle.
Yeah. That's what I was talking about without saying those words. With the wedge overextend over thicken.
I didn't know that could be like linked to tectonic erosion as a process also.
That's the original Montréal. That's the whole thing for Christie.
Right. That's great. The surge of great earthquakes from 2004 to 2014.
Yeah.
That's what that diagram is from? I thought that was from like depth varying rupture properties.
I think that same figure appears in like 10 different papers.
Oh.
Yeah, I just took that one because that's where I found it first this morning.
A tribute to Pore. Is he dead? He's not dead.
No, he's retiring.
Oh, he is?
Yeah.
I didn't realize he was that old.
He is. He's old. He's pretty great. His English has gotten so much better. He's like Oxford now. Before he would just bow. That's cute. It's so nice. Of all the guys I worked with in Japan, he's the one that brings female students to AGU. So
Uchi doesn't bring any female students?
he has any.
He doesn't really have any. At least
I've never met one. No, I didn't mention it.
There weren't any. And, well, I think it was like not a postdoc and like 4 undergrads or something.
Yeah. I don't know how their living works. He said they were super hardworking. They all wanted to get into the master's and there was like one spot.
Yeah.
So they just like studied. They were like going to the field and then studying.
Well, because it sounds like the last year of undergrad is more like a first year of grad school.
Yeah.
Where they really just focus on doing it.
Yeah, great. That's how we did it in Cape Town, and I liked it a lot. Like, all the classes were modular, they lasted 3 or 4 weeks, and then we had like month blocks in the beginning and the end of the year that were just really switched to go see like everyone.
Yeah, it's super fun.
Yeah. But again, we had 3-year bachelors. We graduate 30 people, and then we would accept 16 to do the 4th year. You can't go on to grad school unless you have the 4th year. So the ones that we didn't take back, our own students would have to apply someplace else and check in. But some of them were not really quite ready to do research. So.
And then do you also accept people from other schools to come to the 4th year?
One or two spots. So
It's crazy to me too that other schools have like 3-year PhD, like in other systems, and you have like 1 year master's and 3-year PhD. And 40 years they don't credit.
But then they postdoc for like 10 years because they haven't written up their master's yet when they finish their PhD.
Yeah.
Like, I've had this argument with a lot of your kids over a lot of beers, but
I just feel like it's way too fast, and just in general.
Yeah.
Why push through that quickly? I don't know what the argument is for.
it's funding. Whatever the funding agency says your PhD is funded for 3 years, then
You finish in 3.
Typically, do you think only done in 6 years? Compared to if you do it in the US.
Is this for the skin dry and working?
Yeah.
no, this is a classic.
Yeah.
Yeah, but like as Jamie keeps pointing out to me, like his entire bachelor's was geology. He took nothing else. He didn't even take chemistry or physics or math. Like because
They do that in
specialized in
Canada.
high school.
Right.
Yeah, he went through Calc 3 or whatever in high school, and then he just took. He still like 4 or 5 structural geology classes. And I've had. Of course, like shit like this. Which yeah, so it's just different. But and the problem with the super short PhD is that nobody gets to take a hand in designing their project. It's designed and funded before you show up, and then you just have time to execute it. You don't have time to write. And so forth.
I just feel like then too, like the whole trajectory is like very much like student under very specific direction, and then thrown into a pod stack where maybe you haven't acquired the skills to stack yet.
Right.
So extreme.
As long as the system's internally consistent, see how it all works.
Yeah.
If that's the expectation when you study postdoc, then great, you're ready for
Right.
that. But somebody who comes out here, like in the States, you could legitimately spend 7 years doing a PhD. You know, like that's 7 years of experience.
Yeah.
Not comparable to somebody with 3 years of experience, regardless of what the title is.
Yeah.
Yeah. Matt Tarling did a degree in physics. I think his geology degree of like 3 semesters in our department, and then went to a 3-year geology PhD.
Which university is he at now?
He's at Otago.
Oh yeah.
Yeah, he's doing the Southern Alps stuff with Steve
Yeah.
Smith.
I've seen the photos on his Twitter.
His Twitter is epic.
Yeah.
They have they go up above tree line, the camp, and there's these like little ground dwelling parrots. They come and like attack their kids.
They're crazy.
Yeah, they
The
sound
Keybirds?
psycho. Yeah.
I thought that was some video. The Keybirds will like rip off the windshields on your car.
Yeah.
And
Like
like,
violent,
we were on a
adorable
bus, like
parrots.
the kids would land on the bus while we were stopped, and the driver would like get out with a broom and just be like, "No, don't land on my bus." Like, he'll rip the pieces, I guess. But they're apparently very strong.
The sound that
Yeah.
I mean,
That's
you know,
cool.
we probably have no idea what's going on.
for posterity is being quoted.
Good. Can I ask you a question actually about the diagram that you drew?
Yeah.
Because I feel like you were interchangeably saying that the blue schist grade stuff was sediments, but also pieces of the
Right.
oceanic plate, which is true, but then so in that diagram you draw like little lines within the duplex type structure.
Yeah. Yeah. So in the duplex down here,
Yeah.
like every one of these indicates a time when the fault has stepped down. It doesn't always step down into the ocean in the crust. It can
Yeah,
step down to
sounds
some lower level in the sediment. So yeah, there's places both
It's a mix.
I know of in Japan, Alaska, and California where you have these kind of limited area terrains that have the salt at the base of each imbricate.
Right.
And it's usually something like a few tens of meters of basalt, not more.
Yeah.
So it implies that it's found some kind of either hydrothermally altered or weak layer in the basalt that becomes a favored décollement.
Mhm.
But if you had a slippery bit in the sediments or like, particular bed that was more shaly instead of sandy, like that would be your preferred. I should have said that explicitly. You could have any amount of basalt or.
So like when you get one of these high grade blocks in the serpentinite matrix, are those blocks made up of a mix of like sediment and oceanic material, or is it just the oceanic block?
The ones I've studied only have oceanic.
That's like weird. What happened to the sediment?
I know. I think Vince asked Sam that the other day.
No.
Yeah. you can't even see what's happening in this diagram because they've covered it with wiggly arrows. At some point, there's these green blobs. They're supposed to be oceanic crust rocks. So there's a few wild theories about that. One is the other potential source for serpentine besides the upper plate mantle wedge would be below the oceanic crust. So maybe these blocks enter the system because there's so much serpentinized mantle, maybe from the outer riser and before, that when it starts to destabilize with temperature, when you get down here, that it's actually just falling apart and breaking up the plate.
Yeah.
Possible. Why are there no sediments? I mean, in some subduction zones, there's like basically no sediment subducting, like ocean. And the Franciscan might have been one of those at the very early stages in its history, in which case the problem goes away. But all of that's wild speculation.
I'm good.
Okay, it's 2:51. Fire it up again. Okay. All right. Is everyone ready?
Ready.
Awesome. Okay.
Yep, we're here.
Okay. All right, this is the last section. It might be a little bit less connected than everything else, but whenever I finish this, we're done. We're going home. Okay, so the topics we're going to talk about now is pore pressure effects on faulting. But to talk about that, I had to talk a little bit about the architecture of fault zones, and then I have to show you some more circles. So sorry, everyone, there's going to be more circles. Okay. So this is a diagram from Zoe Shipton and Patience Cowie, and they were interested in looking at the evolution of faults, and they went down into southern Utah. There's all of these beautiful flat-lying layer cake continental sediments out there. And in this area called the San Rafael Swell, there's like a giant antiform that stretches over tens or hundreds of kilometers. And along with the bending of the strata to make this antiform, the kind of some of the layers in there are big, thick sandstones, and they're overlaid by soft shales. And so the little extensional faults that formed along those sandstones when the antiform formed have been beautifully exhumed by the blowing away of all the shale. So you can see everything from a tiny crack that's like starting to grow or connect to other cracks to form a fault that might only have 10 centimeters of displacement on it. And then you go over another couple hundred meters and you find one that's got a meter of slip on it, and you can see where it tails off and it's growing. And then you can find one that has 10 meters of slip on it and it's starting to look like a proper fault. All of these different stages of evolutions of the faults are exposed out there in the San Rafael Swell. So, Shipton and Cowie basically built this cartoon of how faults evolve based on looking at a whole bunch of different faults at different stages in their evolution here. So the amount of slip on a fault is something that you can measure. And we're going to use that as a proxy for what we're going to call fault maturity. So as the fault grows in displacement, it also has to grow in length and in depth along in the dip direction. So all of these dimensions are going to be scaling with one another. And as it does so, it's actually going to change in its morphology, its character, from being a single crack. In theory, a fault starts with breaking a single grain, breaking between two grains. And then different tiny cracks link up. So in A, in the upper left corner, we have the earliest stage of deformation that's forming a brittle fault, where you have individual cracks that have formed and start to connect to one another as they grow. And we talked about deformation bands last time. A lot of the very smallest or most tiny offset structures in a sandstone would be deformation bands, and that's the case where they are working. And so in A, in the kind of pre-fault development or the very initial development of a fault, the deformation dies out beyond the fault tip. So all the deformation is concentrated along the fault. And the little fractures that are around the main fault surface are things that formed about the same time but didn't participate in the linking up. So you end up with one kind of master slip surface that's linked up some, but not all of the fractures there. Okay, as that fault continues to grow or more displacement occurs, we move to cartoon B. So the development of that through-going fracture from the linking up of tiny fractures gives you your fault slip zone. little networks are developing around the fault. You're still developing new cracks around the fault. So you have an array of cracks on both sides of the through-going slip surface. And the distance over which fractures can link up starts to grow. So the more displacement you have in the fault, the more it can recruit farther away fractures to sort of join the party and become part of the fault system. We see that in the cross-sectional view there, where the tip of the fault is propagating down, but there's a whole bunch of disconnected little fractures there that are going to link up if the fault continues to grow. Then moving to C, we've got the fault core itself starts to change when there's more slip in there. Maybe you have more cataclasis and you develop a fault gouge in the slip surface. So that starts to change the permeability and the frictional properties of the fault. You have more linkage with stepovers. So we often talk about things like the primordial roughness of the fault. And if a fault is formed by linking of little fractures that weren't in the same plane with each other, then when they link up, that's going to inherently put steps in the surface of the fault, which are going to give it geometric asperities, or like it'll give it more difficulty slipping. More cataclasis will be required in order for it to slip by each other if it has a stepped surface. And then by cartoon D, we have a well-developed fault. It's cutting all the way across our rock block. It's broken through some of the steps. If you look at the cross-sectional area, the one that's dipping to the left there, you've got some diagonal segments that have broken through to link up across those irregular steps. And so that points to the trend of faults becoming smoother with more displacement, which is kind of mostly true if all other variables are taken into account. A more mature fault would be generally more smooth. There are mechanisms that compete with that to actually roughen faults, but we're not going to talk about those. So here's another famous fault zone diagram, and this is from Jonathan Kane and his advisors working in Dixie Valley, which is it's a big normal fault in the middle of Utah. Pretty spectacular place. It has some of the highest heat flow to be found anywhere that's in the continental U.S. actually. So I think the geothermal gradient in Dixie Valley is about 60 degrees per kilometer, and there's a big geothermal plant right along strike from the fault outcrop where Jonathan was working. But so this is a big normal fault, and on the left we have the protolith, which is tertiary volcanics in this case. And on the right, we have the hanging wall, which is quaternary alluvium. And the throw on this fault is something like 3 kilometers. So it's well beyond the maturity stage of the faults on the previous diagram. So what Jonathan's mapped here on the normal fault scarp, which also happens to be the topographic surface and the outcrop of the Earth, is that there's this thick light gray zone called the damage zone that has lots of this spaghetti on this is representing fractures. So we have a damage zone that has a lot of fractures. In the protolith rock, there's a few fractures. And then we have 2 kinds of breccias that are forming the fault core. We have class supported breccias in darkest gray, and then we have matrix supported breccias in light gray patches. So this basically represents a fault core structure, which is breccias, and a damage zone around it, which is the damage zone. And in fact, in this case, since he's walking on the surface of the Earth, he doesn't see any damage zone in the quaternary alluvium. But if you could get down through 3 kilometers of quaternary alluvium to find some bedrock, you would also see damage zone there, in theory. I think that's what they're tapping for the geothermal plant, in fact. So Jonathan developed this based on looking at the Dixie Valley fault and some other faults. He developed this kind of network anastomosing fault model for the architectural components of a brittle fault. So you have your fault core, which is shown in red, and that can be braided. There can be multiple strands of it that meet and intersect and separate. And those are going to be where you have your most intensely deformed fault rocks, the cataclasites, breccia, and gouge, like we talked about last week. That's surrounded by this damage zone, which is small faults that are synthetic to the main fault, lots of opening mode fractures. And so as a result of that, we have a lot of veins that fill opening mode fractures. And then there are a lot of folds, because this is the material that's softened by the damage of the fault, and it's also in contact with the major fault plane. So there's a lot of drag folds that can form in there. And then the protolith he's got in the gray rock here. So these are kind of the parts of the fault. Here's an example of a damage zone. This is from Heather Savage's work in California, and it's a little itty bitty fault. It's called the low tide fault, and it has a displacement of something like 3 to 10 centimeters on it. And so what Heather's done here is drawn out the fault core. It's cutting some diatenaceous siltstones or something really soft. She's drawn the fault core in red. And then she's traced out in blue all of the little fracture systems around this fault. And what Savage and Brodsky found in this paper, two key findings from this paper. So one is that they compared a bunch of faults that had like real small displacements, 1, 3, 10 centimeters, and going up to like a few meters. And they found that the number of fractures around the fault actually continues to increase as the displacement increases. So that means the fractures around the fault aren't just formed by that initial stage of forming a bunch of fractures and then link up. Patients Cowie and Zoe Shipton had concluded that once you linked up, there was no reason for the wall rock to fracture anymore. So the number of little fractures around the fault should stay constant even as the fault matured. Savage and Brodsky showed that in fact that's not true. There is maturity trend with time. And so here's their plot. On the x-axis is the displacement on the fault. And this is a log scale. So these are going from little tiny faults on the left to really big faults on the right. And then the total fault zone thickness, this is actually the thickness of the fractured zone around the fault. So for the itty bitty faults, they have, if their displacement is in sort of centimeters or meters, they're also getting a total width of fractured zone around the fault that's centimeters or meters. And as the fault displacement increases to 100 meters and even up toward 1,000 meters, toward a kilometer, the fractured zone is increasing in width that whole time. So a fault that has an offset of about 1 kilometer would have 100 meters wide damage zone around it. Okay, so now we've gone from like looking at a couple of little grain fractures, who cares, to looking at a major permeability controlling structure in the crust. The other thing that happens, and they've shown this with a little gray bar here, is there's a rollover in the plot. So as they're going up in orders of magnitude to a 10 kilometer offset, 100 kilometer offset fault, they don't see evidence that the damage zone continues to increase in width. It looks like there's a bit of a rollover and things stay a couple hundred meters wide. And the evidence for this comes from things like observations around the San Andreas fault, where when you're near the San Andreas fault, where we know the rock is damaged, the seismic velocities for S and P are slowed down over a certain width around the fault. And that's attributed to having a lot of open fractures and causing a lot more, what's it called when your wave energy dissipates? Attenuation. Attenuation around the fault. So the attenuation zone around the San Andreas fault is about several hundred meters to sub-kilometer thickness, and that's where it would plot on this diagram. So, okay, so.
Christie, just
yeah.
a question. That previous diagram, is that looking at all sorts of different types of faults, reverse, normal, and strike slip?
It is, and it's
Or
also, it's looking at all types of faults, and it's also looking at all types of rock. So it's nice to imagine or speculate or maybe drive a future project with the idea that you might be able to pull more significant patterns or order out of this diagram if you separated faults and sediments from faults in crystalline rock, for example. They would have different fracture development response to the same stress condition. Yeah. But yeah, I did ask the authors about that, and I got some kind of fumbling answer like, well, we only had a couple of this or that, so we ran out of data if we tried to plot it subcategories. But it feels like something that could and should be done.
Just, I mean, I've seen some examples of thrust faults with, close to like several tens to even maybe 100 kilometer of slip on it, whereby the hanging wall within meters of the fault is totally undamaged and pristine.
Yeah, that's kind of scary.
Actually, the Champlain thrust is a good example, which you may have seen.
Just is a good example.
And the one thrust in Scotland also has the hanging wall. The stratigraphy is preserved. The fossils are happy, and there's no damage yet. There's, 100 kilometers of slip.
I don't remember what is the morning thrust all brittle deformation?
Well, there is a significant ductile component.
Yeah.
For sure. But
I think
yeah.
if we're talking about thrust faults, we might run into the problem of like cumulative displacement versus what's actually contributing to the damage zone would only be maybe the brittle stages of displacement, which would be that's another reason why they didn't go into the subdivisions on the plot. But these are specifically targeting sort of upper crustal. Yeah.
The Champlain Crust, for example, is all brittle.
Well, the footwall deformation is not brittle there.
No, but the hanging wall of it.
Yeah. Yeah. Are you sure there's no damage in the hanging wall of the Champlain thrust? Because it's all recrystallized, at least where I've seen it on the outcrop.
No. I mean, no, I'm not sure. I've not studied in detail, but it just looks pretty happy.
Right. So there's certainly probably faults out there that wouldn't fall on this plot or would fall outside of the expected numbers on this plot. And there are, even if you look at these high displacement ones, there's some of the dots fall kind of low, like the lowest one maybe falls at the 10 or 100 meters. But yeah, so I guess to plot an individual one on here, maybe it's better that this wasn't actually compiled by field geologists because we are sticklers for the detail. But you want to make sure that the displacement that you were using to plot it was all representative of brittle displacement. And you would want to separate the thickness of the damage zone in the hanging wall from the footwall, for example, especially for something possibly like the Champlain thrust, where the hanging wall might have been the leading edge over 100 kilometers of displacement, but maybe the footwall has only seen 10 kilometers of displacement or less. So at any given outcrop. So yeah, there's a lot of complexities that could mess with this relationship. And the rollover is represented by a small portion of the points because they're harder to collect this type of data. The bigger fault you get, like nobody's ever, to my knowledge, walked like a 10-kilometer transect across a fault and measured all the fractures. So they're getting into other types of proxies up there. Yeah, so that's a good point. I don't know where the Champlain thrust would fall on this, but I know Heather's familiar with the Champlain thrust, so I will tell her you asked and see if I get anything interesting back. Okay, so because as an undergrad, I personally was introduced to the Moore circles and then put them completely out of my mind forever, to the point where I told my structural geologist PhD advisor once that I had never been taught this, which was a complete lie because I had a whole notebook of this stuff in my own handwriting, which I later learned to refer to. I am going to go through Moore circles real quick again for you. Okay, so this is showing, this is just a way of plotting what any given stress condition is, and then using some graphical constructions in order to predict whether certain conditions will lead to a fault slipping or not. So the x-axis is normal stress. That's stress acting perpendicular to the slipping surface. And the y-axis is shear stress. That's stress acting parallel to the slipping surface or potentially slipping surface. And most of these faults that we've been talking about are governed effectively by Coulomb friction. And that means that there's a linear relationship where if you hit this threshold ratio of shear stress to normal stress, then the fault will slip. And if your shear stress is not high enough to reach that ratio, the fault will not slip. And most faults, once you actually have a fracture in the rock, they have zero cohesion. So they would follow the lower line on this plot. This is the shear stress equals the friction coefficient times the normal stress. So that intersects the origin, meaning there's no cohesion on the fault. If you had a case like Ashley's plastic blocks that were glued together, or a fault that had been cemented or something so that you had to actually break the rock in order to start slipping, then the cohesion would not be zero, it would be more than zero. So then we would end up with something like the upper failure line on this plot, tau equals mu sigma plus c. And mu, if you want to recall from last week, that's the coefficient of friction, the ratio of shear to normal stress. And that is the number that Byerly measured for all the rocks when he got 0.6 to 0.7 for like all the quartz and feldspar and granite
and sandstone and all the rocks. And then he got something like 0.3 or 0.2 for clays that he measured. So that mu is a, well, as we talked about, it's not always a constant, but it's a characteristic of individual minerals or rock. Okay, stress states are represented on here with a circle. So the principal stress axes that we define are the, well, they're the coordinate system that's our reference. They have the maximum, minimum, and intermediate stress. And so there's no shear stress resolved in that direction. And that's why the maximum principal stress and the minimum principal stress, sigma 1 and sigma 3, they both fall on the axis, on the horizontal axis on this plot. And we draw a circle there to represent basically shear stress going positive, which is going to the left, and shear stress going negative, which would be going to the right. But there isn't really negative shear stress. It's just the same shear stress, or same magnitude acting in the other direction. And so that's why we multiply theta by 2 so we can go full circle in this plot. But within the stress conditions represented by sigma 1 and sigma 3, we can have any fault of any orientation plots on there. We just plot it according to its angle relative to the maximum and minimum principal stress. And so one radius here that I've put on the diagram represents one potential fault orientation. And by using this kind of configuration, we can see exactly what the normal stress and shear stress on that particular fault would be. So if I go from the black dot that is on the circle where it's intersected by the radius, then I could go over to the vertical axis and read off the shear stress at that point, and go to the horizontal axis and read off the normal stress at that point. So if I knew mu and c, if I knew the properties of the rock, of the fault that I was interested in, I would know whether that shear stress and normal stress ratio was enough to cause failure. So here we are, both plots together, and that particular one intersects the failure condition. It does for a fault that has some cohesion and some coefficient of friction. So that fault would be capable of slipping. But the little dot to the right of it, that doesn't have enough shear stress to normal stress ratio, because the normal stress for that guy is higher. So that fault cannot slip under these conditions. Okay, so this is the key. The reason why I'm going through all of this is to remind you of the role of pore pressure in the faults. Because if you have some stress condition here with, on the right, which I've called stable, that stress condition is going to have no slip on the faults because it's nowhere near the failure envelope. The key thing that pore pressure does is it presses out evenly in all directions against the confining stress in the rock. And what that does is effectively lower the normal stress, but it does not affect the shear stress. If the shear stress is set by the ratio of the circle, what the peak shear stress is, and the circle stays the same size, but increasing pore fluid pressure causes that circle to shift toward the origin on the normal stress axis. That means something that was previously at a stable stress condition, once you insert a higher pore pressure, and again, that doesn't just mean inserting fluid. You have to confine that fluid. It has to be increasing in pressure. You shift that circle over, and the circle can intersect the failure envelope, and then you have a condition where the fault's going to slip, even though it should have been tectonically stable. So this is from Jonathan Kane again, talking about the role of pore pressure changes in controlling the seismic cycle. In a particular fault, in this case, he's talking about that Dixie Valley normal fault with the high geothermal gradient and the hydrothermal system active along the fault. So in that case, the fault always has a source of fluids coming up from beneath. And when the fault is not closed, when it's not locked, you get hot springs all up and down the surface. And there's beautiful silica sinter deposits, and occasionally there's actually a hot spring that you can visit along these faults in Nevada. But those hot springs have a lot of dissolved solids in them. As they come up the fault, the fluids cool down and they depressurize, and that means all of this mineral material that's dissolved is going to come out of solution. And the net effect of that is to seal up those fluid conduits in the fault, to cause veins to precipitate where there were open fractures. So Jonathan's got two stages here. The interseismic period at the top, he's got The fault, he's got a little damage zone around it, and he's got some little tensile veins that are represented by these little kind of light gray cracks. But the fault core might be an open conduit. It's under compression, but there's fluid coming up through it. And then the more cemented up it gets, the more that pore pressure increases, the more the stress state moves toward failure. And then at the bottom, the two diagrams there show the co-seismic event where basically you fracture the whole system because you've moved it to intersect the failure envelope. That allows those pressurized fluids to vent, and the pressure drops in the system. And he's represented that by forming these vein cemented breccias, these light gray breccia bodies with the big dark clasts in them that rupture right across the fault, break open the fault zone. They cause more fracturing in and around the fault zone. And then you have a period of enhanced permeability in the fault where the fluids can vent comfortably until they basically self-shut down the system by cementing up their own fracture conduits. And there's a lot of systems where this is called fault valving. It was actually described first by Rick Simpson, but maybe you're having Simpson overload by now, or it was named by Rick Simpson. This kind of fault valving, or the cycling between elevated pore pressure causing a rupture, which causes permeability increase, which drops the pressure and allows the fault to slip, and then eventually the fault heals again and recycles. This is responsible for the formation of things like low gold deposits, big bull quartz veins, and stress cycling in fault zones. So this is something we can actually track really well in the rock record because of this nice cross-cutting relationships with all these fractures and cements. So this is this figure here, maybe Jonathan's most famous work. He's a great structural geologist and he's done some economic geology work, but this is probably what he's best known for, is taking the fault core in the damage zone and looking at the range of how different fault systems might work. So what we've got here is, this is basically like a plot. So damage zone permeability increases on the vertical axis. So the top examples have high permeability in the damage zone, and the bottom examples have low permeability in the damage zone. And then on the horizontal axis, we have the permeability of the fault core. So the fault core has low permeability on the left and high permeability on the right. So it's basically like a grid. We have four possibilities and combinations here. So if we start at the upper left, we have a case where you have high damage zone permeability, but the fault core permeability is low. And he says this is maybe characteristic of accretionary prisms or subduction systems, places where you might have, instead of having like a big breccia in the fault core, maybe you have a clay smear in the fault core, something that stops fluids flowing, but surrounded by open fracture zones so the fluids can flow around the fault core and basically up the fault. When we move over toward the top right, we have the combined conduit barrier, which is this Dixie Valley example we just looked at, where you have a lot of fracture permeability in the damage zone, and you might also have, at least transiently, high permeability through the core as well. And this could be something that cycles in time, particularly with the amount of fluid supply or the amount of cementation that goes on. If we continue around clockwise and go to the lower right, we get the localized barrier. So this is a place where you might have high, I think barrier and conduit, well, just backwards. Anyway, a localized barrier would be a place where you had low permeability around the in the damage zone, but you had a high permeability through the fault core. So this would be something where if the fluids were moving up the fault, they would move easily through a high permeability corridor. But fluids trying to move across or into the fault would hit a low permeability damage zone. So that would create a barrier. And then the last one, the localized conduit, would be a place where you have low permeability in the core and low in the damage zone. So this would be the time when the only time you would have fluid flow would be favored or voluminous through this fault would be during periods of fracture or rupture. But during most time, you have low permeability in both. So this way of thinking about faults as conduit barrier systems, either changing in time or space, has really been really influential in thinking about the hydrogeology of fault systems. So when we think about this, like we have different scientific tools to investigate it at different depths. And the depths we're interested in are quite different for different reasons. So we go through 2 texty slides here, but the first thing, we're going to make an assumption that, which is probably true, that below the water table, that is as soon as you hit groundwater, everything is saturated. All the rock pores are full of water and all of the fractures are full of water. So everything we're standing on is wet at depth. So the upper kilometer of where is the water, where is it moving, is basically the realm of hydrogeologists. Like structural geologists don't really go there because it's dirt grade. But you can study this basically by putting wells down basically to hundreds of meters or a kilometer. So you can directly sample the rock. You can, in many times, map pathways through it by testing pump tests between one well and another to investigate what the character of the rock is, how important fractures are in connecting one well to another versus individual pore flow. You can recover samples of the rock. So by drilling or by sampling at the surface, you can characterize what the material is like at depth. Yeah. And then as you get deeper, so below about a kilometer, we no longer have a lot of direct sampling or the capability of doing direct measurements. So it becomes the realm of shallow geophysics. And so you can use things like conductivity, resistivity, density, gravity surveys, and reflection seismology or refraction seismology to start looking at what the structures are and making inferences about the amount of pore fluids present, what those fluids might be, and how they're moving. I guess some oil and gas drilling goes to these depths, so there's probably a lot of data there that we don't always get access to. A lot of the fluids in this point are approaching supercritical. So in the top kilometer, we're looking at water, and it has the properties that we're familiar with. But as we get deeper, we start to look at hybrid fluids, a lot of dissolved or two-phase flow that really changes the effective permeability of the systems. And fluids with like very low surface tension, which changes how the fluids can move through pores. And then when we get deeper than that, we're really looking at inferences that geologists can make. So we can build on the geophysical methods. It starts to be really useful to look at exhumed structures to understand what we're looking at. And by about 5 kilometers, most of the fractures are actually closed because of the lithospheric load. So we have more of a pore dominated or transient fracture dominated permeability system. I just wanted to mention hot springs for fun. So this is a little diagram from the Utah Geological Survey. It's the same setting of a basin and range fault as what we described for the Dixie Valley case. But a lot of the water in these systems is actually basically local meteoric water that's driven directly by the topographic gradient that's created by motion on the fault. So in this Wasatch Range in Utah, it's the edge of the Great Basin and Range. And because of the orographic effect, they get a lot of rain in the mountains. It filters down through fractures and pore systems in the mountains. Encounters hot rocks because of the high geothermal gradient, goes across the fault into the footwall or the hanging wall rocks, which are alluvium and have much higher permeability, and then escapes up the fault. And this is why the Basin and Range is basically a terrific place to go hot spring, to go find hot springs. But it also drives this whole cycle of cementation and rupture that was described in the fault valving mechanism. Yeah. Last important point I want to make is that knowing where the fluids are does not tell us necessarily where we have high pore pressure. So this is a plot of seismic velocities, or anomalies in seismic velocity from Cascadia. And what these authors were trying to do, this is Jeff Abers et al. In 2009, what they were trying to do was look for areas of high pore pressure that would explain why tremor occurs where it does on the Cascadia subduction zone. And again, the sources of fluids to the system are going to be all those things we talked about in the subduction. So the pore fluid that's subducting, mineral water that's coming off, maybe organic fluids. But as we're getting quite deep here on the horizontal axis, 50 or 60 kilometers, we're mostly looking at mineral derived fluids, if anything. So what these authors found is if you look mostly just focus on the upper plot. So yes, it's more obvious. There's a red swath, like a big red area that starts near the 20 on the vertical axis and then continues down dip. And that line is continuing down. That's basically the plate boundary interface with the Juan de Fuca plate on the left and below, North American plate on the right and above. And so this big red area here is showing areas where the S waves are very slow in the crust, and it's right on top of the plate boundary interface. And it's also where all these green dots are showing earthquake epicenters, and where the histogram at top is showing a lot of tremor activity. So the authors here inferred that the presence of fluids is enough to slow down the S waves. And so this is a map of basically fluid concentration and other things. And they inferred that this high fluid concentration is related to high pore pressure, which is probably right because those fluids are probably confined, but it's not necessarily the same thing. So I just want to like drive that point home once more. It's like fluids are not necessarily at high pore pressure. In fact, if they were at high pore pressure, you'd expect them to migrate. So maybe this is something that should change with time, depending on what the flux of the fluids is through the system. Okay, that's it. I'm done. Any questions?
Hi, Christie. It's Jane.
Hey.
Hey, I have a question regarding the schematic diagram of CAN 1996. Why it's defined as a localized contour when probability is low in both the fault core and the damage zone? I got a bit confused in the definitions of barrier versus contour in this context here.
So, yeah, the paper goes into some detail about this, but if they're both low, well, okay. The detail that's not actually shown on this particular plot is whether you're considering flow along the fault or across the fault. So in this case, the overall structure would give you more preferred flow along the fault, even if the permeability was low in both. It would be more permeable than going across the fault, just because of the alignment of the structures.
Okay, so this is permeability, I guess, across fault permeability or fault parallel permeability? There.
It's not uniform across this diagram. So I think, yeah.
Okay, I'll find the paper and read.
Okay.
Yeah.
Yeah, so I think all these four categories could be defined specifically either for a long fault or a cross fault flow. And these are just end members. No one fault is going to be uniformly one of these types all along and across it. But this is actually one of the cool papers that's a real crossover paper between geology and hydrology. The hydrologists have adopted this maybe even more than geologists have. Yeah, but it's a interesting way to think about it, and especially to import it into things like thinking about fault valving in the earthquake cycle. Versus how someone would act on the time scale of like trying to use it as a water supply, for example. Right.
I think it's a very useful diagram for me in terms of thinking about induced earthquakes.
Oh yeah.
Yeah.
Sorry,
so I'm going to find the paper and read.
Okay, it's in geology, so it's only 4 pages.
Okay.
Any other questions? No. Okay. Okay. Apologies to all the students. I did not post the quiz yet, but I will go to my office and finish writing it, and you will have it.
Okay, well, there's no questions at our end, Christie, so either students are just way too shy or everything's crystal clear. So.
One or the other.
Crystal clear at SFU.
All right. Thanks, Dan. Okay.
Thank you very much, Christie.
Bye, everybody.
Bye.